according to our best models of physics, the ones that predicted black holes before we ever found one. There is a hard limit on how fast any object in the universe can grow. It's called the Eddington Limit, and something has broken it completely. Imagine discovering a man walking down the street. He's healthy, lucid, moving with purpose, and then you find out he's 500 years old. Not metaphorically, literally. Born before Columbus reached the Americas, still alive, still walking. That's not a metaphor. That is, essentially, what astronomers confronted when they measured Phoenix A, a black hole so massive, so impossibly, grotesquely, mathematically forbidden, that our entire understanding of how the universe builds things doesn't have a satisfying answer for how it got there. This is the story of the most dangerous object we've ever found. Not dangerous because it will reach us, but dangerous because of what its existence might mean for everything we think we know. The universe waited 13.8 billion years to produce something like Phoenix A. You don't need to wait that long. Subscribe to the channel and leave a like. Phoenix A sits at the center of the Phoenix cluster, a massive galaxy cluster roughly 5.8 billion light-years from Earth, and it is heavy, 100 billion solar masses. Let that number land for a moment. 100 billion suns. For context, our own Milky Way's central black hole, Sagittarius A, is about 4 million solar masses. Already incomprehensible. Already a thing that defies human imagination. Phoenix A is 25,000 times more massive than that. If Sagittarius A is a freight train, Phoenix A is the planet it's traveling on. Astronomers classify black holes above a certain threshold as ultra-massive. Phoenix A doesn't just clear that threshold. It practically defines a new category. Some researchers informally call it, and others like it, stupendously large black holes. A phrase that sounds almost comedic until you do the math and realize no other description fits. It was identified through X-ray observations and later confirmed through detailed measurements of the surrounding galaxy cluster. The data was unambiguous, the mass was real, and then the question arrived, quiet, disturbing, and still unanswered. How did it get there? To understand why Phoenix A poses a problem, you need to understand the Eddington Limit. In the early 20th century, British astrophysicist Arthur Eddington derived a theoretical ceiling on how fast a gravitational object can accrete mass. When a black hole eats, when it pulls in gas, dust, stellar material, that process generates radiation, enormous amounts of it. And that outward pressure of radiation pushes back against the infall of new material. At a certain point, the radiation pressure equals the gravitational pull. That's the Eddington Limit. Beyond it, the black hole can't efficiently eat anymore. The feast becomes self-regulating. The system throttles itself. This isn't a law that applies in some exotic corner of the universe. It's a fundamental physical constraint derived from the interplay between gravity and radiation. It applies everywhere, which means black holes have a speed limit for growth, and the universe has a finite age, 13.8 billion years. That is how long the cosmos has existed. That is the total time budget every object in the observable universe has had to do anything. Form, collapse, merge, evolve, grow. If you take the Eddington Limit seriously, and you take 13.8 billion years seriously, you get a ceiling on how massive a black hole should possibly be by now. Phoenix A doesn't just approach that ceiling, it punches through it. If that idea made the back of your brain tighten, you're not alone. Subscribe. We go deeper every week. When astronomers first confirmed the measurement, there was no celebration. There was a silence that tends to fall over a room when the data is telling you something your models say is impossible. The universe apparently didn't receive that memo. So how do you build something this large in the time available? 3 pathways have been seriously proposed by researchers. The first is sustained super-Eddington accretion. In certain extreme conditions, dense gas environments in the early universe, chaotic gravitational configurations, a black hole might be able to eat faster than the limit allows, at least temporarily. Radiation leaks out in jets rather than pushing uniformly against infall. The geometry allows more material to reach the event horizon than classical models permit. This is theoretically possible, but sustained over hundreds of millions of years at the scale required to produce something like Phoenix A, the numbers become uncomfortable. The second pathway is mergers. Black holes don't only grow by eating gas. They also grow when galaxies collide and their central black holes spiral together, merge, and combine their masses. Given enough time and enough collisions, you can stack mass quickly. The problem is the timeline again. The mergers required to assemble 100 billion solar masses from plausible seed black holes in the early universe demand either an implausibly perfect sequence of events, or they demand that the universe started with something already far larger than our models predict seeds should be. Which brings us to the third pathway, and this one is the most unsettling. What if the models are wrong? Not wrong in a small, correctable way. Wrong in a structural sense. Wrong about what the universe was doing in its first 100 million to 1 billion years. An era we can barely see, filled with conditions we're only beginning to model. The James Webb Space Telescope has already found black holes that are too large, too early. Quasars that shouldn't exist yet, sitting at redshifts that place them in the universe's infancy. Phoenix A is the most extreme case of this pattern. It may be the signature of physics we haven't written yet. Here is what we don't know. We don't know how the first black hole seeds formed after the Big Bang. Most models assume they started relatively small, the collapsed remnants of the first stars. But some researchers now propose direct collapse scenarios, where enormous clouds of primordial gas bypass star formation entirely and collapsed straight into massive black holes in a single event. If those seeds were large enough, and they accreted aggressively enough in the dense early universe, something like Phoenix A becomes marginally less impossible. Marginally. We also don't know if the Eddington limit is as absolute as it appears. It's derived under assumptions that may not hold in extreme environments. If early universe accretion was geometrically or thermodynamically different from what we model, the speed limit could have been effectively higher. And we don't know how many objects like Phoenix A exist, because we've only surveyed a fraction of the observable universe. Because the measurements required to confirm ultramassive black holes are at the edge of what our technology can do. Because there may be things out there larger than Phoenix A's, sitting quietly in the dark, waiting for a telescope pointed in the right direction. What keeps researchers awake isn't Phoenix A itself, it's the implication. If one object can violate our timeline this severely, if one black hole can grow this fast in a universe this young, then something fundamental about how we model cosmic evolution may be incomplete. Not wrong at the edges. Wrong somewhere closer to the center. Tell me in the comments. When you think about an object that shouldn't exist but does that make you doubt our models, or does it make you trust the universe more? I read every reply. The universe is 13.8 billion years old. That sounds ancient. In human terms, it is beyond comprehension. It is a span so vast that every civilization that has ever existed on Earth represents less than a rounding error on the timeline. And yet, apparently, it is not old enough. Not old enough for Phoenix A to exist. And Phoenix A exists. Which means either the universe has found a way to work faster than we thought, or the universe has been hiding something from us since the beginning. and we've only just started to notice. Keep looking up.